Hello everyone. We're on our 12th lecture on asynchronous processing. Last time we talked about choosing a database, and that was the last in that long sequence of lectures on databases. And we talked about several different kinds. They varied in terms of how scalable they were, and they also, for the ones that were scalable, these ones in the middle, the various NoSQL databases, I showed many different varieties of NoSQL database, and the biggest difference between them was in the way that they structured the data they stored, and that affects the kinds of requests that you can make to the database and the kind of requests that are well supported. I also showed how distributed file systems are actually very similar to distributed databases in the sense that you can think of a file system as storing a key value pair where the key is the file name and the value is the data itself, the data of the file. But it's the simplest kind of database because you don't have operations that manipulate the individual parts of the data. You have to use these low-level open and read through the whole data kind of operations, the whole file. We also talked a little bit about transactions for the first time. Transactions are really well supported by SQL relational databases. It's easy to support a transaction when all your data is stored in one place. With distributed NoSQL databases, transactions are also possible on many of those databases using conditional write operations to implement a lock. But that really slows down your interaction. So even if you are using a NoSQL database that supports that kind of transaction, you should try to avoid it. And you often can do that by, I guess, allowing inconsistencies and then resolving them later on. All right, so today we're talking about asynchronicity. It's a new topic, and it's a new chapter in the book. So make sure you read that. It's a pretty significantly sized chapter in the book. So far, we've talked about coupling client-server systems by in the simplest possible way, in a synchronous way, where we send a request to the server calculates the response, and the response gets sent back, and the client kind of waits for the response before it moves on. HTTP and REST are designed around this model because, in the sense that they provide for a response to be sent back that has a code for whether it was successful or failed, and the data that you request comes back in a response. But the client we say this is synchronous because the client waits for the server to finish the work that it asked the server to do before it moves on. Okay. And that's okay, and that's the most popular kind of client-server interaction. But there are cases when it doesn't work well, and particularly if the request is really long. So, for example, if the client makes a request to send an email, the mail server that receives that message has to do a lot of work to deliver the message. So actually, the mail server that the sender sends it to has to forward the message to another mail server, often to more than one mail servers before finally reaching the final recipient. So there are many messages that are sent. And if you made the client wait for all that to happen before telling the client that the message was delivered, that would be a really long interaction. And the client, it might not be a good design if you're designing this API to support a user interface that a human is using, because it would cause that UI to stop and wait for a long time and say, okay, delivering, and then finally tell you it was delivered. The user may not really care so much whether that delivery was successful, and they certainly don't want to wait for that long period of time. So generally, it's nice to have a response, but if it's going to take us a long time, if we're going to have to wait a long time for that response, then we might be better off breaking the connection between client and server and using an asynchronous interaction instead of a synchronous interaction. Okay, that allows the client to move on and do other work, and in this example, for the user interface to move on and assume that the message was already delivered or is on its way. So the asynchronous alternative to this design from an API perspective is for the client to send a request to create an email to the server, and for the server to start that chain of work that's needed to send the message. But once it starts, to turn around and immediately give a response back to the client saying that it was successful. Now, of course, this response doesn't really tell the client that the mail was delivered, but it tells the client that at least it is acknowledging that the message was received and that progress is being made. Okay, so this is a response that says, okay, I'm going to try to send a message, basically. So the advantage of this approach is that the client can now move on to do something else. The client knows that the server is trying to deliver the message, so it can move on. But the disadvantage here is that the client doesn't really know whether the request succeeded. So this is a kind of a fire and forget kind of interaction. Notice, of course, that you could also imagine a design where there was no acknowledgement sent back at all, where the client just sent a message. But that's not good, because the message could be lost in transit, or the mail server could have been down, and you want the client to at least have some confidence that things are making progress. So this is kind of like there's a little bit of an acknowledgement sent, but not a total acknowledgement. Okay. When we moved from that first synchronous interaction to the asynchronous interaction, some things stayed the same, other things changed. So in both cases, we actually stuck with the HTTP REST style of interaction, where we have requests and responses. So we still have a client-server interaction. But the big difference here is in the meaning of the request and the meaning of the response. Okay, so with a synchronous style of API, the request in this particular case was to deliver an email, and the response was an acknowledgement that the delivery happened. So the response is a delivery receipt. So basically, the server is saying your message was delivered to the receiver. With the asynchronous style, we still are giving a response that is meaningful, but it's a different kind of response, and the request is a little bit different. We can change the semantics of the request to match the asynchronous style and to have this request response interaction still be meaningful. So instead of previously we were asking for the server to deliver an email, now we're telling the server to send an email, which is to say try to send an email. And in that case, the response can be okay even if the work is not done. So the server says, okay, I will try to deliver this email, or I will send this email. Or you could say forward instead of send. That might be a little more clear. But the point I'm trying to make here is that the semantics of the API are different when you move from asynchronous to synchronous. You still have a response, so there is some synchrony here in the asynchronous style of API. In other words, the client does expect something to come back, and it waits for this response to come back. But the response has a different meaning, and it's a more concise meaning that that can come back more quickly. Okay. Now, that works well for reducing the delay experienced by the client, but it introduces a problem, which is the client doesn't know what happened with the email in this case. All right, so we call that a fire and forget kind of interaction, where the client sends a message and it doesn't ever learn what happens with it. That's not going to be good enough for every case. So some APIs are designed as fire and forget APIs, but sometimes we do want the client to be able to asynchronously access the results. So we want the client to proceed asynchronously, but we also want it to get access to the results. The client should be able to later find out whether the request succeeded, and maybe even to get some data back from the response. So I want you to stop and think about how you can support asynchronous access to the results in an API that's asynchronous. So please pause and think about that. I'm going to provide two different ways of doing that. So the first is a request record, which is a term I just came up with. It's not like a standard term, but the idea is pretty simple and common. This is that you create like a record in a database for the work that's ongoing, and you check back in that record. So this API interaction, I'm showing the API calls made by the client in this case. First, it posts a message attempt to the mail server, and the response it gets back is an ID. So the server again says, okay, I'm going to try to deliver the message. But in addition, it says that this is message number 4390293. Now, that this doesn't mean the message was delivered. It just means that this message has an identity to it. So this is like a tracking number for the request, right? In order for this tracking number to be useful and to have meaning later on, the server also needs to store this tracking number, this request record, in a database, because later on the client is going to send a request to get the status of that request. So it can, let's say there's an API that looks like this: get /message/status/ the request ID, and the response at first might be that it's pending, like it hasn't been finished yet. But eventually, at some point on the back end, the response is going to be finished. And when that happens, that whatever process it is, whatever service that's disconnected from the client that finishes this request, it was given the request record ID, and it can actually update the database with the fact that the request was finished, and also it can provide some data that might be available now for that request. So later on, the client has to keep asking, and eventually when it asks, it'll get the real result from the request. In this case, there was a status of failure that was stored, and there was like an error message that was given. So originally in the synchronous design of the API, this failure and invalid address message would have been returned immediately from the first request. Instead, I'm using an asynchronous style where the client proceeds and it comes back and checks later. Now, one problem here is that the client doesn't know exactly when it should check, so it has to keep checking and checking, and hopefully, that's actually introduces some extra work. It's not really efficient, and so there's a trade-off between the inefficiency of extra requests and the delay, like the extra time you're waiting to get the response. But it does support this asynchronous style well. Okay. You may have thought of another option. Well, maybe not. This one's a little bit more complex, but this is for the client to provide a callback function. And by function in this case, this would mean a probably what's called a webhook, which is the URL for a REST request that's going to come back, or any kind of network request that the client specifies. So the client creates the request, but which is shown down here in the first bullet point in the bottom half here. But in addition to providing the message, the client is also providing a callback URL. So basically, the client is saying, here's a message for you to deliver, and also here is the URL that I want you to send an HTTP request to with your results when you get them. So this is telling the server basically who the server should tell when it's finished. And this message can be propagated throughout the system to the service that eventually handles and finishes the request. So the client sends this, provides additional information in its request, which is the callback URL. The server fulfills the work, and then when the server is done, the server will make a request to this URL, providing the information and the status. Okay, that seems like a good design, but the challenge here is that most clients don't really have the ability to listen for messages. Like if the client is a web browser, for example, it's making HTTP requests, but web browsers don't run servers to listen for, to handle requests, right? They're not web servers. So in a web browser, this would be difficult to support. The only useful alternative, doable alternative would be to use WebSockets, which maybe we'll talk about in a later lecture, or use some kind of push notification, but that's not exactly a client. That's a different style. Yeah. But if the client was some kind of a back-end service, it might very well be able to easily handle one of these callback requests. And this also, keep in mind that this callback request could be could be the address of a different system, but as long as that system is kind of connected to the client in some way, that design can work. All right. And there are two variations here. This callback could be provided in the request, or it could have been provided separately in a registration request that associates all of the responses for this user to a certain URL. A third option, which is a little bit hacky, but very common is to use some kind of side channel for feedback. So in this case, we have clients do fire and forget requests. But when there's a failure, we don't really report it back to the client, but instead we report it back through some side channel. In this case, the example I'm giving is placing an order in an online store. So you might be purchasing a book. The website might say that it's proceeding, that it's going to place the order, that your request is all good. But then later on, in fulfilling that request, the system may realize that, oh, actually we're out of stock, or actually your credit card is overdrawn or something. So later on, there might be an error, and you could return that error to the user through email. In this case, if you have the email address of the user. Now that's not really an API level thing, but that's why I call it a side channel. But that's definitely a legitimate strategy that's used for a lot of kind of systems. The response also could come through in some kind of log that developers or operations staff or customer support staff at the company are looking at. So if these are, the point is this works really well for unlikely failures. So if we expect these things to happen most of the time, once in a while they'll fail. And when they do fail, let's say a person should deal with it individually, then we can use one of these side channels for the feedback. Right. All right, so I want you to stop and think now. We've talked about asynchronicity. The examples I gave were sending an email and purchasing an order in an online store. What other kinds of requests in a scalable system might benefit from asynchronicity? I want you to stop and think about that for a minute. So please do that. All right, so basically these are going to be things that take a long time in general. So really, and also things that could fail at a later time that's unpredictable, or things that could take a long time for either because of the processing involved or because of the human systems involved, which is So the example of an example of a thing that takes a long time computationally might be transferring a file over a network. I mean, it's not really computation, but it's storage and network that is going to make it slow. Fetching a file from tape storage. You probably don't even know what tape storage is, but accessing data in a system that has to move mechanically is that example. Creating a virtual machine. So on AWS, when you create an EC2 instance, when there's an API for that, I mean, I know that you use the user interface to do that, but there also is an API to do that, and you'll get a response immediately saying, okay, we're going to create the virtual machine. It takes several minutes to create that virtual machine. So what you get back is, I'm not sure, it might give you an instance ID immediately, and you can check on that instance ID later to see if it's running yet. So that was the request record type of response propagation. Purchasing a shopping cart, we gave that already. Booking a flight or a sports ticket, making a LinkedIn connection request. These are all things that require something to happen in the real world. Like someone has to deliver the item you bought. Someone has to maybe accept your LinkedIn request. In the case of booking a flight, the reason why this has to be asynchronous is because there often are several backend systems that need to communicate. If you're using orbitz.com to book your flight, Orbitz has to contact, let's say, American Airlines to make sure that your seat is still available, and there's a whole back and forth there that takes a long time. Yeah, and we'll see later on that creating a tweet, if you have a lot of followers, is something that would take a long time and therefore should be asynchronous. And the final examples here are for gathering analytics that aren't needed immediately. So for example, if you're using Google search and you clicked a certain result, the fact that you clicked that result number 3 is information that Google would want to refine their model for what the best results are, and also to learn more about your personality. Now, that information is not needed immediately, but it's going to use that information later on in their kind of machine learning algorithm to build their models. So that click information can be sent asynchronously back to Google for them to process later. Same thing for an online store like Amazon.com. If you search for, let's say, dog toothbrush, You, of course, want to see the results immediately, but again, that's also information that is going to be used to build a model for the customer to help them recommend products to you. So that search information also can be should be sent asynchronously to the recommendation system to refine their model. Okay, so these are not urgent requests, and it's going to take the effect that that information is going to have on the system is long term and can be delayed. All right. So asynchronicity, we talked already about designing APIs to be asynchronous to give responses immediately, even though something is going to happen in the background. But we haven't talked much about how that work happens in the background. You originally might think about maybe a thread being created in the software that runs some background work. But at a system level, we have message queues usually to provide asynchronicity and decoupling between services. So a message queue is just like the queue you learned about in data structure. It's a first in, first out kind of structure. You can push items onto it, and then you can dequeue items from the front. You can kind of pop off the front and push on the back, first in, first out. And this allows you these message queues allow you to store messages which encode work that should be done later on. Okay. So message queues are kind of like our data structures to help you implement asynchronicity and to decouple services. These are fast to use because we're just copying data. We're not doing any work in the queue, just accepting data. It's kind of like a database. And this allows you the front end to proceed even though more work is going to happen later on. So this example here shows a mobile Twitter app that's posting a tweet. The Twitter API is giving a response pretty quickly saying, okay, your tweet has been created. But the work that goes into publishing that tweet could take several minutes, actually, for it to go through all the different steps. We'll see why it might be slow to tweet. And so to handle that tweet, the tweet is actually put into a queue. Once the tweet is successfully stored in the queue, this API gives a response back to the client saying, okay, your tweet is done. It's not really done. There's more work to happen. But that work, there's a publication service later on that eventually will accept that tweet and do all the work that needs to be done for that tweet to make it really published. Okay. So by doing this, we're preventing slowdown of the upstream service due to like a lot of work that needs to happen downstream, and also allows us to smooth out to accept bursts of traffic, even though this downstream service might not be able to keep up immediately by just storing things in the queue. Right. Okay. So message queues store requests that are ready to be handled but are not yet handled. We call the things stored in these queues messages. And these messages, the format of these messages define the request entirely, right? So the message format is equivalent to an API. So the rules for formatting messages are a contract that's very similar to an app's API. So essentially, instead of this publication service providing an API that this Twitter API calls, instead of making a REST request directly into the publication service, if it could have been designed that way with a microservices architecture where you have many services back in the back end, and you would use REST or some other network API to interact. That API would have to be clearly defined so that this other service could use it. Instead, we're putting a queue in between, and we're defining the message format for messages that need to be stuck in the queue. That's a contract that has to be obeyed by the producer of messages and also the consumer. So you can have different services, different implementations of this service that are written and interchanged for each other. As long as they understand the same message format, they can implement that service, right? Just like you can have an API that's defined and then implemented by different teams to do the same thing or in different languages or whatever. Okay. All right, a little bit of terminology here because there are many different variations of words that mean the same thing almost. We have producers and consumers on each side of the queue. The producer pushes messages or produces messages or publishes messages. Those words all mean the same thing. And the consumer pulls or pops or consumes or subscribes to messages. Those are all words that are related to consuming messages. Okay. And another term you might see is topic. So a topic is a partition of the queue. It's like a category of messages in the queue. It's a way of taking one queue and creating several virtual queues that are assigned, that have different purposes and might have different producers and different consumers assigned to them. We call those topics. So that's the reason for that is because we sometimes use a single queue for many different things, just because we want to share the resources here, and this could be actually a big system. We'll talk about that later. But in your designs, you could think of a queue. When you draw queues in your design, depending on what level you're working at, you could actually just draw multiple queues, one for each type of message, and each one would store a different type of message. But then you could, in practice, store those all together in the same queue if they each are put under a different topic. Okay. And so consumers can subscribe to just one topic or a subset of topics. Yeah. Sorry, there's a little bit of a confusing terminology here because I'm using the Twitter example, and the consumer is actually called the publication service, but this publication word here should not be confused with the publishing that the producer is doing. So this producer is publishing to the queue. This publication service is publishing to Twitter. So this is don't confuse that. Sorry, maybe it was a bad example for that reason. All right, so let's see how this queue is used in this very simple example. The first thing that happens is that we have the mobile app that does an API request to create a tweet, right? Post tweet. The API on the backend gets that. Just as a example, one of the things that might happen is that this API has to check to see whether this request is valid and it should be handled. So there's probably some kind of authentication token that's included in this request. The Twitter API, this is a microservices architecture. There's more than one service. So this service contacts another service to ask it whether the authentication token is valid. This authentication service has to check a database to see whether that matches a user. In fact, it does. So it gets back the user ID that's associated with this request and gives that back to the API. Okay, so that was a synchronous interaction that happened between the Twitter API and the authorization service. Similarly, there's a synchronous interaction between the authentication service and the database. Once that gets back, this Twitter API can proceed with the work of servicing this tweet, but it's decided to do this. It's designed to do this in an asynchronous manner. So what it does is it creates a tweet creation job, which is a message. It puts that message on the work queue, on this message queue here, which is called I've called it the work queue here, and that'll be processed later. But since once it gets an acknowledgement from the queue that was received, it can turn around and tell the mobile app that its job is finished. So it can send back a success message to the app saying that your tweet was handled successfully. Now, I want to ask you, was this premature? Should it have waited? Why did it give a response so quickly? Stop and think about that for a second. In fact, it is a little bit premature, but this is what it's doing here is using an asynchronous style, and so it's using that trade-off of giving a response immediately, even though it doesn't really know the tweet was created. It hasn't stored the tweet in all of the followers' feeds or anything like that. It hasn't done push notifications when necessary to the followers. But at this point, we can reasonably surmise that this API backend is very confident that eventually this tweet will be published, because it did check to see whether the user is valid. It's not a canceled account. It's not an invalid credential or anything like that. So with 99.999% confidence or whatever, this thing is going to get published. So in other words, it checked that the request was a good request, and it's acknowledging that it was a good request and that in all likelihood it's going to be published. So this is a pretty good design for this purpose. And that's why we actually did the synchronous check with the authentication service instead of, you could have actually deferred this authentication until later on, after pulling the message off the queue, but then the client might not the client would be missing some common useful feedback. Like, for example, if the app timed out, like if you were inactive for too long and your session's no longer valid, so you basically were logged out. If that's the case, then your tweet is going to fail, and you don't want the user to think that the tweet succeeded, even though it's not going to be delivered because you were logged out. Okay. So we queued up the tweet creation job. Later on, this publication service is going to fetch that job off of the work queue. It's going to go through them in a roughly first out manner. So it fetches a message. It sees that this message is a published tweet job. It knows how to handle that because this is the service that you've designed to connect to this queue that has that kind of message. To implement that, it has to check some databases. So the message that was stored here encodes all the information that's needed to get this work done. So part of that is the content of the tweet, also the identity of the user that did the tweeting, right? So this publication service is going to check to see who all the followers are of that user. And now it knows it has to update all the followers' feeds with this new tweet. So it might go through and store in all the feeds of the followers the new tweet from this user. Now, it might also need to send push notifications to all the followers if those followers have configured push notifications for this particular user. Like if they have alerts enabled for this particular user that made a tweet, then they should get a push notification. That could be a lot of work because there could be a lot of followers. So what I'm doing here in this design is creating a separate message for each one of the followers that needs a notification. That's going to be a subset of all the followers. And those can happen later, and they're also not critical, and it could be slow. Like if you're doing notifications over email or over in the mobile app, each of those are done in a different manner, and also could be a large delay for that. So it makes sense to maybe have a different code base that handles that, because it's a lot of work that could be separated into a different code base. So that we're using this queue to separate the basic concerns of publication with the notification code and the work of notification. So finally, this notification service in a similar way pulls jobs off this notification queue, and it probably will have to check a database. So these jobs that are queued here will indicate which user it is that's getting a notification. That user probably has stored whatever their preferred notification method in a database that has to be checked. And then finally, this notification service has to implement that notification somehow by contacting an outside service, which I haven't tried. If there's a failure delivering this notification, you have a few strategies. You could retry a few times and then give up. That's a pretty reasonable thing to do. Now, you don't notice that there's no feedback to the original user if any of these later steps happen, but that's okay for this particular application. Like the user, when they're sending a tweet, doesn't need to be told that a particular follower is not going to get a push notification for that tweet. Like we just let that failure be silent. Okay. So when we're designing asynchronous systems, there are trade-offs. I've kind of talked about these already. In a tightly coupled synchronous system, we have a simpler design, but there could be some slowness in the interactions that for doing work that takes a long time. In loosely coupled asynchronous systems, we can get faster responses, but then it's harder to see what happened. Like it's harder to get responses back to the client. Those might be ignored. We could have some strategies for dealing with them, with those responses, but it's a lot more complicated. We also need to build a more complex system that includes a queue and multiple services instead of having just like a one monolithic synchronous service, right? There also are significant scaling benefits to using queues and decoupling services with queues, okay? So a message queue, you can think of it as being a simple kind of database. So it's an external system apart from your application servers, and it stores data. The data it stores are messages. You can think of those as rows in a table. You don't have all the power of a SQL relational database, but you have the ability to add things and to remove things. Like a database, you can have many producers connected to the queue, and you can have many consumers connected to the queue, right? And these consumers, for example, should be stateless so that any one of them can handle the messages, just like a bunch of app servers behind a load balancer. Okay, so this message queue acts like a load balancer in the sense that it allows work that's stored in the queue to be distributed among a bunch of different consumers that are like taking turns getting messages off the queue. Okay, whoops. Notice also that you can scale the producers and consumers separately and dynamically. So it might be that the amount of work done by the producers requires 5 of those to be running, but the amount of work done by the consumers is less, so you only need 3 of those to be running. So you can monitor those and scale them separately. You also can use these queues to smooth out demand peaks by deferring work. So if during a busy time, there might be a lot of production happening, a lot of messages being created, a lot of things that need to happen. If those things are not time sensitive and you have the capacity in the queue to store them, you could just let them build up here. And the consumers, even though they're not capable at peak time of handling the throughput of messages being produced, you can keep them busy 24 hours a day by having the queue grow during the peak time and shrink during the off-peak time, right? So you can save some money that way by smoothing demand peaks. All right. There are 2 basic styles of queues in terms of how the messages are consumed. So, and I call those passive and active queues. It's a pretty simple concept. It's not terribly deep. But with a passive queue, the queue accepts and stores messages until they're requested, and the consumer has to actually request or ask for messages. And it typically would do that periodically, or it might do that like sequentially. Like the consumer might ask for a message, process the message, and once it's done, it asks for the next message, and then it processes it, and then asks for the next message. And eventually, it might go back at some point and ask for a message, and the queue would say there are no messages, and then it would try again later, right? So that periodic requesting of messages is called polling. And with that kind of passive design, the queue, it's passive from the perspective of the queue. The queue isn't really doing anything except accepting messages and then responding to requests from the consumers. So messages are being pushed into the queue and pulled off the queue. So I'm calling this a push and pull model. However, we can also have a push-push model, which I'm calling an active queue. In this design, the queue actually is programmed to know who the consumers are. So when messages come in, when it has messages, it can actually push out messages to the consumers. In that case, we more often use the terminology subscriber for the consumers. So the queue actively pushes messages out to the subscribers. The difference in architecture here is that the subscribers have to be listening for messages instead of, so the subscribers act like servers instead of clients, I guess. I'll make a note of that to update the slides. Yeah. But, some queue software is designed for one model or the other, but a lot of queue software is designed to support both of these modes of operation. All right. So queuing is a general concept to support decoupling and asynchronicity, and it can work at many different levels of your architecture. You can have queues in your code, like in your Java code. You can have multiple threads that are working kind of in parallel in a decoupled manner and use a queue to synchronize work between them. The executor service can do that. You might have even done that for homework 1 to handle processing the work files. You can have a separate queuing app that runs on the same machine that accepts requests over the network, the virtual network in this case, and then does something with them. So it might be that queuing app might be handling the interaction between 2 applications on the same machine, or it might be handling work that's eventually going out to an outside system, but you're queuing it up before it gets sent outward. An example of this is Netflix's Suro software, which actually I worked a little bit on contributing to. And finally, and most importantly, we have distributed message queues. Examples of these are like Kafka and SQS and RabbitMQ, ActiveMQ. These are big external systems that are kind of like distributed databases. So there are many nodes implementing this queue, like a distributed database, like a NoSQL database, and they can handle a ton of traffic coming in and going out. And this allows all their work to go to one big queue. And it's robust in the sense that because it has multiple nodes, it has redundancy built in, so when a node can fail, and it's scalable to handle a ton of traffic. Okay. So these using queues at different levels have different pros and cons, and really, I mean, it's not really a matter of choosing between these, because you don't have to choose between these. You can use all of these, but they have each of them has different advantages, I guess, like and characteristics. So an in-app queue usually is in memory, so it's fast, it's easy to use, but it's not backed up to disk. So if the app crashes, if you've taken advantage of an in-app queue, you might have a lot of work that's like in progress that hasn't been finished, and so you lose work when your app crashes. If you're using a separate queuing app, one of the benefits there is that they're usually designed to write messages to a file, so that if something goes wrong, you have a backup of that messages that are in flight. But on the con side, your scalability is limited to one machine. So if your machine or disk fails, then your system goes offline. So you lose availability, and you might also lose some messages if it's a permanent failure of the machine. Finally, we have distributed message queues, which give you the most power. And these are like building blocks of really big systems. But it's complex to implement one of these, unless you actually use a managed one, like Amazon SQS gives you the benefit of a distributed message queue, but without the cost of having to deploy one yourself. But the cost you pay is that they charge you per message for using it, so there is a kind of like monetary cost to it. Another downside of distributed message queues is that, just like a distributed database, they have some consistency issues you have to be aware of. And it's pretty typical, for example, for you to have to choose between messages being delivered at least once or at most once. You can't get exactly once, but you really want for messages to be delivered exactly once. At least once or at most once means, at least once means that in order this is to tolerate failure of nodes. If they implement some replication, then the system can be designed, the way the systems are designed to make that replication work, because the failures can happen right in the middle of something when they're not sure whether it finished or not. It's possible that an operation will happen multiple times, and a message will be processed multiple times. So if you're going to use that kind of a system with that kind of consistency in the queue, you should design your messages to be idempotent. So if they're run multiple times, it's okay. Like you can if you have a record to create an order in the database, if you have a message that creates an order in your system, it should have some ID or something, so that if the order is created again, it overwrites the last one, or it recognizes it as a duplicate and throws it away, in the final processing steps. The Flipside design for consistency is for messages to be delivered at most once. What this means is they might not be delivered at all. So what this is saying is that if you want redundancy, you have to accept the fact that you might have things happen more than once. But if you don't have redundancy, then you could drop messages once in a while when there is a system failure, which is not a good thing. Okay. So an example of a distributed message queue is Kafka. And it has some additional features. So, for example, messages are kept after they're read. The reason for that, so it's not just a first in, first out queue where the messages are consumed and thrown away. It's more like a distributed commit log where things are kept. The reason why they keep things around is so that later on you can reread the same data again. So this is designed for data that where the consumers are not just like handling work and then the work is done, but rather the consumers are analyzing a history of events, and you might have different things that need to happen. with those events. So those events might be read by, let's say, the payment processing system and also the order fulfillment service, and then also by an analytics engine that generates statistics on these different things. And those processes all would consume the data, the same data, multiple times, but with different lags. So this picture down at the bottom shows the Kafka log, where we're writing new data to the end, and then so the producer is adding to the end of the log, and we have two different consumers at the same time that are subscribed to this data that are reading left to right, and they'll actually all read this data. So the same data will be read twice by two different consuming applications. These are not replicas of the same application. These are two different types of application. Like one of them is the invoice service consumer, the other one is the push notification service consumer. So they're doing different like business functions on the data. So we have multiple producers contacting it, and there are many nodes in the system, like that use something like a distributed hash table to divide the data into different commit logs that are on different machines to give it scale. And notice also that with this kind of a system, you don't have a true ordering. So it's not truly a first in, first out system. Because you're storing the data in different places. So if you're using a distributed queue and you're implementing things that need to happen in a certain order, then you need to be careful, and maybe you need to combine those things into one big message instead of having two small messages. Like for example, if you're sending two different emails to the customer, and one of them says your order was placed, and the other one says that your order was shipped, you don't want those to go in, like, you don't want them to be delivered in the wrong order. So if you want to be confident, if it's important that they're delivered in the right order, you could combine them into one message. You'd have to combine them into one message, and then have the consumer implement them like in serial, one at a time. Okay. So with queues, there's always the possibility of the queue filling up and running out of space in the queue. When that happens, there should be some kind of back pressure, or there is some kind of back pressure to prevent producers from adding their new data. They can't. If the producer tries to produce more data, it'll fail because the queue can't store it. I'm talking about queues in general now, not Kafka in particular. So there should be the possibility for some kind of error response to be sent back to the producer. But the system usually is not designed to handle this, and it's a bad thing when it happens. So in practice, you usually have your DevOps staff monitoring the size of queues to like operationally determine whether the system is running well, whether there's an imbalance between producers and consumers. If they see the queues start to build up, they should add more consumers to shrink the queue, right? To pull stuff off the queue. Also, one of the things that students last time were confused about in using queues in their architectures was I saw some students try to put queues like at the front end of the system where, like, let's say a React app was sending something to a queue. That can't happen directly, just like databases, which this also might not be obvious, but both databases and message queues are, I would say, back-end creatures. Like the APIs they have are not designed to handle connections from public, unauthenticated clients, nor from thousands of clients. So these are designed to be to accept messages from other parts of your backend. And if your front end does need to create a message in a queue, it should do that through some kind of intermediary API. Okay. So finally, I'm going to go through a little example to motivate why Twitter was designed with queues and asynchronous processing in the first place. And I guess maybe this could have come first in the lecture anyway, but to reinforce that, let's imagine a design of SQL of Twitter with a SQL relational database. And this is how it was originally designed, and this is how I would probably design it if I was starting off from scratch and just wanted it to be as simple as possible and wasn't really anticipating having, like, millions and millions of users, but just wanted to get a minimum viable product. You have a table with users, and you have tweets. Every tweet has a user associated with it, which is the sender ID. So this 12 here matches this user 12. And there also is a follower table, which shows all of the relationships between followers and followees. So in this case, Jack is followed by user 17055506. Now, what we have, this scenario we're looking at is when this user 17055506 logs in and wants to see their feed, their Twitter feed. In order to do that in this simple design, the user has to write a query, has to execute a query, or the user makes an API call, and that API has to build the feed, has to do a join of all of the tweets that match users that this logged in user is following. So it's a join between the follower table, like basically there's a subset of the rows in this follows table where the follower ID matches the current user. And for all of those, there has to be a join of the followee ID and all the tweets that match it, right? So there might be like, let's say there are 100 rows in this table that have 17055506 and then some different username as the followee, as the person who's being followed. For each of those followees, you have to go in and find the tweets that match. And then you kind of sort them according to timestamp to get the feed, right? So the read operation is pretty complicated. That checking your feeds is slow, but writes are fast. So when you do a tweet, it's really easy to handle that. All you have to do is add to this tweets table, one row. Okay, so this system is optimized for writes, for tweets, but those are like maybe 100 times less common than these tweets that are slower, right? So this design is concise, it's simple, it's easy to understand, it takes up very little space, so it's efficient in that sense, but it's really inefficient in terms of handling reads, okay? So the solution they had to fix this was to pre-build the feeds. So instead of doing a join every time to get the feeds for users, they pre-build the feed. So they have already stored in a database every user's feed, and that includes duplication, right? Because every tweet that you see in your feed is seen in lots of other users' feeds if they're following the same people as you, right? So this is a denormalized design that matches the NoSQL style, right? So these feeds can be stored in a NoSQL database. That can make it scalable. So this gives you some scalability benefits, but also even if you weren't using NoSQL, just this concept of pre-building helps with reads, to make reads fast, but it introduces duplication. Okay. So whenever a user tweets, whenever there's a write, you have to not just write to that tweet once in the database, but you have to write it to all of the feeds of users who are following that user. That user, yeah. So if this user posts a tweet, it goes to their own like log of tweets, but it also has to be sent to the feed of all the followers. Okay, so that's okay if there are only a few followers. But if you're a celebrity and you have like 31 million followers, let's say, you don't want that user, that very important user, to their phone to have to wait for 31 million things to happen on the back end every time they tweet. And for a response to come back that says, okay, now your tweet's done because now we copied your tweet to 31 million followers feeds, right? So that was a motivation for why we moved to why Twitter has this asynchronous design. So this design I showed before, where is it? Yeah, I just wanted it on one screen. The reason why there's this queuing and building of feeds later in the publication service is to make writes fast. I'm sorry, to make writes fast in this design scheme where there's where the feeds are pre-materialized, pre-built. All right, so we talked about message queues today, and asynchronization in general. We showed how APIs can be tightly or loosely coupled, and we can describe those as synchronous or asynchronous. With asynchronous calls, we get faster performance. We get an immediate response, but that response doesn't tell us much, right? So there's a trade-off between getting a quick answer and getting a good answer, right? At one extreme, we don't get any information at all, and we call that a fire and forget request. Well, we also have ways of creating request records in the database or getting a callback if we do want to get some information later on. So APIs can be asynchronous. We also can use queues to build asynchronicity into services, where we define APIs in terms of the format of messages that are sent in the queues. So queues act as a kind of load balancer for deferred work. Instead of work being handled immediately by someone that you explicitly call, you put the work in some queue, and then the worker later gets the work off the queue and handles it. But we don't know exactly when that's going to happen. So we have producers and consumers separated by a queue. They can be scaled separately, and as long as they agree on the format of the message, the system works well. We can use queues at many levels. Inside an application, you can have a queue in memory. We can have queuing apps that run on a machine, maybe alongside some other applications. And finally, we can have distributed message queues that implement huge scale, but which have some consistency trade-offs. And particularly the ones I mentioned before was that messages are usually implemented at least once or at most once. You can choose between one or the other, but you cannot choose to have messages executed exactly once, which is what you really want. So that's a consistency trade-off there. All right, so that's all I have from this lecture.